So I'm going to talk about my work with my advisor Shubhangi and Narmada, who's also a PhD student at University of Toronto. And it's on reconstruction of depth 3 arithmetic circuits. I would like to thank the organizers for inviting me and organizing this workshop. Also, thanks to Rafael for advertising the talk or scaring people from it. We won't be using any strong algebras, only linear algebra in the talk. So, so we all know what arithmetic circuits are. So let's start with what reconstruction is, right? So reconstruction, you are given a polynomial which is computed by some circuit C from that comes from some class script C, and what you're given is you are given black box access to evaluations of this polynomial. You pick any point and you will know whatever the polynomial evaluates to on this particular point, right? And what is the goal? The goal is to output a circuit that efficiently computes the same polynomial as the input circuit, right? And if you add another restriction that this circuit, the output circuit, is also from the same class where the input circuit was from, we call this particular problem as proper learning. And this is the version of learning that actually works for arithmetic circuits. And why? Talk to me offline, right? If you think for a minute, you will see that deterministic reconstruction is harder than de-randomizing PIT, right? And even worse is historically what we have observed, that the classes that we do know randomized reconstruction for, to get randomized reconstruction, we have required stronger structural insights to the model than that were just required for PIT. And reconstruction has connections to lower bounds. If you get reconstruction algorithms, you can get lower bounds. You acquire deterministic reconstruction, but there are some connections known in this line, but I personally think it would be really interesting to know more of these connections. What I'm going to focus more is on trying to solve this problem for low depth circuits, right? So let's try to do reconstruction for small depth circuits, and let's start with the very basic. Start with depth 2, and the very basic depth 2 model is sigma pi, which is your dense representation, your sparse learning, and we all know this problem as multivariate interpolation. We know how to do this in polynomial time thanks to Benoit-Thévary and then Clarence-Spielmann, and so we have polytime algorithms for this. Again, it's not trivial. It does require some interesting ideas to be able to do reconstruction even for depth 2 circuits. If it's a pi sigma circuit, it is basically the question is you are trying to factorize the polynomial you are given black box access to and get black box access to the factors. This was done by Carl Toffen, and then we know a lot more about factoring, but the factoring talks on Friday, so we'll see it there. But once you move to depth 3 circuits, it becomes extremely challenging for sigma pi sigma circuits, and challenging enough that here's an open problem that just a depth 3 circuit with top fan in 2, and let's say fix the number of variables to 5, the degree is increasing, give me a proper learning algorithm. When I say proper learning, I mean the top fan in for the depth 3 circuits is also 2. We don't know how to do it. A simple small circuit, we don't know how to do how to do proper learning for it. And another reason why depth 3 reconstruction is very interesting is tensor decomposition, a problem we listened to a lot about yesterday. And so you are given a tensor and you have to find the minimum R such that the tensor is a sum of rank 1 tensors. And if you think of finding the task of tensor decomposition in the algebraic complexity world, it is basically, the question is of reconstructing or proper learning depth 3 set multilinear circuits with if the tensor has rank R, then the set multilinear depth 3 circuit has top fan in R. And a lot of some work has been done using, where you have considered this exact model, and we have some really interesting algorithms for tensor decomposition in certain parameter settings that goes through exactly reconstructing depth 3 set multilinear circuits. And that brings me to the point where I will tell you why we should not do this now, because it's hard. Well, first is we all kind of know about depth reduction. You can squeeze any depth circuit into depth 3 with subexponential blowup, which basically means if I can do polytime reconstruction for depth 3 circuits, it gives me a subexponential reconstruction algorithm for general circuits, which is probably very hard. So, you don't, it's probably going to be hard. A close problem to reconstruction, which is pack learning. If you can give a polytime pack learning algorithm for depth 3 circuits, it starts breaking cryptographic primitives. So again, possibly not, that something that's very hard. And as we just discussed, proper learning for set multilinear depth 3 circuits is tensor decomposition, and Johann Hartstadt showed that tensor decomposition is NP hard. So, this is also probably hard. So, depth 3 circuits is hard. So, what are we going to work on with? Well, we are going to work on with a restriction. What are we going to restrict? We are going to restrict the top fan, right? So, the circuits we are interested in, they get, we are going to restrict it to some k, and these circuits are basically sum of k terms. Each term is a product of linear forms, and that is what we are trying to reconstruct. We would be describing them as sigma pi sigma k. And one thing we will do is, you can you can simplify this computation a bit by taking out all the GCD, putting it in G, and then looking at the remaining part. I don't think you see the pointer, but the remaining part, it's what we call as the simple part. So once you have taken out all the GCD, you look at the remaining gates, and that is the simple part. And a quantity that we would care a lot about this is the rank of the circuit. As I think Rafael talked about it a bunch as well, but just in case you missed it, it is basically you look at all the linear forms in all the gates that are in the simple part, and then you consider the space they are spanning, and the dimension of the space is basically the rank of your circuit. And this is a very important quantity for depth 3 circuits, and we'll see why in a minute. Before we go into reconstruction, as we talked, it's more harder than PIT. So what do we know about PIT for these models? And as Rafael talked earlier, these do find really interesting connections to problems in discrete geometry, and specifically what is these Sylvester-Gallai configurations, right? What does that even mean? Well, just consider, top fan in is 3, and you have a top fan in 3 depth 3 circuit that is computing an identity. Just think of so it basically means you have 3 gates, T1, T2, T3. Consider the linear forms in T1 to be red points, T2 to be blue, and T3 to be green, and pick any 2 points of different color. Pick L1, L2, which are red and blue, and then consider the circuit mod this ideal, right? Consider C mod L1, L2. Clearly T1 will vanish, also T2 will vanish, so what we will be left with T3, and that basically means that T3 mod L1, L2 is 0, and since the ideal generated by L1, L2 is prime, that means there's another point that lies in the span of L1, L2, and so there must be some L3 that lies in the span of L1, L2. And this is a huge restriction, right? You pick any 2 points of different colors, and there must be a point of third color that must lie in the span. And this is what we just learned in the morning. Is called the colored high-dimensional version of the Sylvester-Gallai configuration. People love it. They have studied it in much detail. And what they have showed is that if the points have these kind of restrictions, they lie in a small dimensional space, right? And a long line of work that Rafael talked about in the morning did end up culminating in around 2013, giving us a black box PIT algorithm for these kind of circuits, depth 3 with constant top fan-in. And one pattern that you might see in all these results that kept reoccurring was that if the circuit is computing an identically zero polynomial, then the rank that we just discussed a few slides ago is gonna be low, right? And what I mean, let's say the field was reals, then it just means it's gonna be 3k squared. So you had k times d linear forms, each of them dependent on n variables. It does not depend on n, it does not depend on d, it's just gonna be a constant, it's gonna be a 3k squared, it's gonna be a small space, and yeah, this is a really nice structural result. And so, you know, the question for PIT for this model is kind of solved and been solved for 13 years now. So what do we know about reconstruction then? Has that been studied? And it has been. The first 2 papers talk about reconstructing this when the field is kind of small and they do have you know, a quasi-poly dependence on the size of the field. And then if you remove that restriction, what else we know? We only know reconstruction when the top fan-in is 2 or 3, and we didn't know anything else. One thing I would like to tell you is all these algorithms, they only do proper learning when the rank is high, right? And so what is our result? Our result is, you know, for the purpose of the talk, think of the field to be rationals. And the circuit that we are going to look at is constant top fan-in depth 3 circuits. I'm saying think of it rationals, but any field that has, you know, is characteristic 0 or characteristic at least d works, and we give a randomized quasi-poly time reconstruction algorithm, and this reconstruction algorithm is it does proper learning when, again, the gates are high rank enough. And this is the first subexponential reconstruction algorithm that we know in the setting for depth 3 constant top fan-in circuits. So that is our big result. And for any questions? Good. So now I will try to give you an idea of how do we do it, right? And what problems we face. So the main outline of the proof is, you know, what we do is at the start, we prove a bunch of structural results about the polynomial that is being computed by the model we are interested in. And what we do then is use these structural results to learn a few linear forms that happen to be inside the circuit somewhere. And then we learn the entire circuit using the few linear forms we learned inside the circuit. So I want to talk first about step 3. Why? Because I didn't do it. It was did by Shpilka and Karnin-Shpilka. So to understand what they did, consider a top fan-in 2 circuit. You have red and blue points. And let's say you have a friend who looked inside the black box and saw a red point, saw L1 and told you what it is. What you can do with this point? You can consider the circuit mod L1, and that gives you the gate T2 mod L1 because T1 vanishes, right? So you learn a projection of the gate T2 mod L1. And let's say your friend was really nice and he just didn't give you one linear form, he gave you log D independent linear forms, and you use them to get log D independent projections of the gate T2. And what Shpilka showed was that that is all you need. That is enough information to learn T2 up to a constant, and this was a really nice result that used lower bounds on to query LDCs, and yeah, that is how you did reconstruction. And then Karnin-Shpilka generalized this idea to be able to learn from projections of constant top fan-in circuits instead of just one gate. And one question you might have is, where are we getting these linear forms? I don't have any friend looking inside the black box. So what Shpilka and Karnin-Shpilka both do is they find the bunch of variable reductions to log D variables, such that if you can do reconstruction there, you will be able to lift it to the original one. And once you are in the log D case, variate case, you basically brute force over all linear forms that are in the field that depend on log D variables, and that is where you get the quasi-poly in the field size running time. And you can naturally not do it for infinite fields and large fields. So where do we get our linear forms? We get our linear forms from something that we will call as vanishing spaces. So what is a vanishing space? Let's fix K to be 3 for understanding purposes, and our vanishing space when K is 3 is going to be the set of codimension 3 spaces on which this circuit will vanish. And what could be such spaces? Well, one such space is, just pick 3 linear forms, one from each of the gates. You set all these 3 to 0, they vanish each of the gates, so your polynomial vanishes. So if you consider C mod this ideal that's generated by L1, L2, L3, it's 0, and this space, the codimension 3 space, that is, whose kernel is generated by L1, L2, L3, is a vanishing space for our circuit. Let's say we are not happy with just one such space. We get another such space with some different blue and green points, L2 prime and L3 prime, and let's say they are all independent. So you have another vanishing space. You set these 3 to 0, again the circuit vanishes. And let's say I have access to all codimension 3 spaces, so I know these 2 spaces. Then if I have this strong assumption, then what I can do is I can intersect their kernels, and the intersection of their kernels will give me L1, right? It will give me a red linear form. That is what we were trying to do, right? We were trying to find these linear forms, and if we find the set of spaces, that gives us a linear form. So now our goal is from learning a linear form to finding these vanishing spaces, the set of vanishing spaces. And we'll call it SK, which is the set of codimension K vanishing spaces. And the first question one might have is the set even finite, right? And it naturally isn't the way it is defined yet, because, well, you can have a purple point in the mix of greens, it's not independent. You have a L1, you have an L2, and this guy is which is an L1 plus L2, and when you go mod L1, L2, the circuit vanish. So if I'm trying to find a codimension 3 space, the third linear form is anything. Pick whatever you would like, right? But this is not a big issue, because L1, L2 are still linear forms in the circuit, and you can just handle it by adding another word in your definition, which is maximal. And you say that we will only look at vanishing spaces that are not contained in the smaller vanishing spaces. But until now, we are only looking at spaces where each of the gates individually are vanishing. So all T1 to Tk are vanishing. But does that need to be the case? Is it the thing that needs to happen, that individually all of the gates need to vanish? And here's an example where it's not true. So here's a depth 3 degree 3 top fan in 3 circuit. You go mod x2 minus x3. x2 minus x3 is nowhere in the circuit, and none of the gates will vanish individually, but if you add them up, it vanishes. So it's a linear form that divides the circuit, but it will not be, so it's like a S1 space, but it is nowhere to be seen inside the circuit. And this is S1, then you move to S2 and more complex things will happen, S3 worse, and SK, it's gonna be a whole mess. So now a proof outline. At the start I told you we'll be doing some structural results. The structural result that I was talking about was showing that these set of vanishing spaces that we just defined is not only finite, it is polynomial in size if the circuit that we started with is high rank, and then we give a way to compute this set. Not only that it is poly in size, we give a way to compute it efficiently, and then we use these spaces to learn like some polylog D independent linear forms from one of the gates, and then once we have done that, you can learn the entire circuit using the techniques that we just discussed from Shpilka and Karnin-Shpilka. So yeah, that is the main outline of our algorithm. What I'm going to talk about is step 1. So if you think about S1, S1 is very easy to bound because every linear form that you set to 0 such that circuit vanishes must divide the polynomial, and a polynomial can only have d factors, so it can only have d such spaces. So our interesting case is going to be S2. Well, S2 is also, if one of the gates is going to vanish, that will be the easy case. So what we are going to look at is the case when no gate vanishes mod the vanishing space that we are looking for. And what is happening in this case? You started with a circuit that was high rank. You mod this code, you went mod this ideal generated by L1, L2, and then the circuit became low rank. Why did it become low rank? Well, it is an identity. It vanished, and we just learned that PIT implies that if it's an identity, then the rank needs to be low, right? So this is what happened. So you had this circuit, again, let the top fan be 3, and which was high rank. So you have a bunch of points that were in a high dimensional space. You went mod L1, L2, and the circuit became low rank. How can that happen, right? None of these gates have vanished, right? That is our assumption. And you are only setting a 2-dimensional space to 0. So how can the rank crash a lot? And the answer is these points are no longer in the simple part, right? They changed their colors and they became, as you went mod L1, L2, they changed their colors and they all became red. So they moved into the GCD, and that's why they don't contribute to the rank. But this is a great structural condition. Why? Well, you can pick, let's say you have 3 independent linear forms, LA, LB, LC, that became the same linear form. When you went mod L1, L2, then what you can say is the 3-dimension space collapsed into 1. When you mod a 2-dimension space, so the 2-dimension space must be inside the 3-dimension space. You pick another such space. The 2-dimension space should also be inside this, and that basically means that the 2-dimension space is exactly equal to the intersection of these two 3-dimensional spaces. And so once you fix LA, LB, LC, and LA prime, LB prime, LC prime, you also fix S2 space. And that basically means that the number of possibilities of these 2-dimensional space is at most d to the 6, right? Because each of them can only have d choices. Right. So this is a really nice thing that we can show about S2. Does the same thing work when we try to work with S3 and higher spaces? And it almost does, right? But it doesn't. So Why? Well, it can have these kind of spaces which will have this structure. They have one linear form. You go mod this linear form, and the circuit now is low rank, right? It can happen. And what we just saw was, we were only able to bound S2 when the rank was high. But if you are just looking for S3 spaces and you had one such linear form, how will you bound the S2 spaces if it's not high rank, right? And in comes what we call as crashing spaces. So this linear form is a one-dimensional crashing space. So what are crashing spaces? Crashing spaces are these minimal dimension R spaces, such that if you go mod them, the circuit becomes low rank. And then what we do is we define a version of vanishing spaces, which was pretty much the same that we just discussed, maximal codimension R spaces. But we have another condition that the kernel of these vanishing spaces don't contain any crashing spaces. And this is one of the big main theorems of our paper, where we were able to show that the depth 3 circuits, if they start with high rank, then these set of vanishing spaces, which avoid the crashing spaces, this is polysize. So this is the actual result. And now our proof outline also changes. We just discussed that we were able to bound the SR prime when the circuit has high rank. But now, if we are trying to compute, we will have to try to compute SR prime. And to compute SR prime, we'll need to avoid crashing spaces. So first we need to compute crashing spaces. And then, we also need to avoid these spaces while we are computing SR prime. And the rest of the two steps, learning the linear forms and then learning the entire circuit from few linear forms, pretty much are the same. I will not go into details of any of the steps. If you are interested in anything, come talk to me. So some potential future works that I think would be very interesting. The first is understanding what the complexity of reconstruction exactly is. Like in which models it should be hard, in which models it should be doable. Now we have depth 4 quadratics PIT, as Rafael talked about. So, we can try doing reconstruction there. Proper learning when the rank is small is an open question, as I talked earlier. Everything we do, we need to start with a high rank circuit, and what happens when the circuit is low rank, we don't know. And there are other two questions about if we can de-randomize our algorithm, and we can give an algorithm that also works over low characteristic fields, and those would also be, I think, interesting. Finally, I'll be on the postdoc market next year, and be very happy to talk to anyone if you have positions available. And thank you for attending and listening.